Here in the quiet hum of a laboratory somewhere in New York, scientists have just solved a puzzle that has frustrated quantum computing researchers for decades. They took two ordinary elements, germanium and gallium, and created something extraordinary. A material that conducts electricity with zero resistance while remaining perfectly compatible with the same manufacturing processes that make your smartphone. It sounds simple, almost mundane, but this breakthrough quietly dismantles the biggest barrier standing between us and computers that could reshape everything we understand about reality itself. Welcome back to another gentle exploration of the universe's hidden workings. I'm here to guide you through one of the most significant technological leaps of our time, one that's happening not with fanfare or headlines, but in the patient, methodical world of materials science. Tonight, we're diving into how a seemingly small change at the atomic level is solving quantum computing's greatest challenge, and what that means for the future unfolding around us. Before we begin, find a comfortable position. Let the weight of your day settle into whatever surface supports you. We're about to embark on a journey through the intersection of the impossibly small and the infinitely consequential. And while the science we'll explore is precise and rigorous, the implications stretch far beyond any laboratory, touching the very nature of how we might compute, communicate, and understand our place in the cosmos. To understand why this breakthrough matters, we need to step back and appreciate just how strange quantum computers really are. Unlike the device you're listening to this on, which processes information in definitive ones and zeros, quantum computers harness something far more ethereal. They use quantum bits, or qubits, that can exist in multiple states simultaneously. Imagine a coin that's not heads or tails, but spinning in the air, embodying both possibilities at once. That's closer to how a qubit behaves, and it's this quantum superposition that gives these machines their almost mystical computational power. But here's the challenge that has plagued quantum computing since its inception. These delicate quantum states are extraordinarily fragile. The slightest vibration, the faintest electromagnetic field, even the thermal motion of nearby atoms can destroy the quantum coherence that makes the computation possible. It's like trying to balance a soap bubble on a feather while standing in a hurricane. The technical term for this destruction is decoherence, and it happens so quickly that most quantum computers can only maintain their quantum states for microseconds before the information dissolves back into classical, ordinary physics. This fragility has forced quantum computer designers into an arms race with entropy itself. They've built elaborate refrigeration systems that cool their processors to temperatures colder than deep space. They've isolated their qubits in vacuum chambers and electromagnetic shields. They've developed complex error correction schemes that require hundreds or thousands of physical qubits just to create one reliable logical qubit. All of this engineering virtuosity has been necessary because the materials themselves, the physical substrates on which quantum information lives, have been fundamentally incompatible with the robust, scalable manufacturing processes that built our modern world. And this is where our story takes an unexpected turn, because sometimes the most profound revolutions begin not with a dramatic breakthrough, but with someone asking a deceptively simple question. What if, instead of fighting the limitations of our materials, we could engineer new ones that are inherently more suited to quantum computing? What if we could create a substance that bridges the gap between the exotic physics of quantum mechanics and the practical realities of mass production? The answer came from an unlikely marriage of two elements that, individually, are quite ordinary. Germanium, a semiconductor that's been used in electronics for decades, and gallium, a soft metal that melts in your hand. When researchers at New York University and the University of Rochester began doping germanium with gallium, replacing roughly 1 in every 8 germanium atoms with gallium, something remarkable happened. The resulting material became superconducting at achievable temperatures while maintaining all the desirable properties of a semiconductor. Now, you might wonder why this particular combination matters. The secret lies in something called molecular beam epitaxy, a manufacturing technique that allows scientists to build crystal structures one atomic layer at a time. It's precision engineering at the scale of individual atoms, like constructing a cathedral using tweezers to place each grain of sand. This level of control was impossible with previous methods that relied on bombarding crystals with dopant atoms, inevitably creating defects that destroyed the delicate quantum properties we need. Take a moment to consider the scale we're working at. The quantum effects we're harnessing occur at dimensions smaller than the wavelength of visible light. At these scales, the classical physics that governs our everyday experience gives way to something far stranger and more fluid. Particles can exist in multiple places simultaneously. Information can be instantaneously shared across vast distances. The very act of observation changes the nature of what's being observed. Traditional approaches to quantum computing have tried to impose order on this quantum chaos through brute force. Superconducting quantum computers, like those built by Google and IBM, use Josephson junctions, electrical elements that exist only in the realm of superconductors. These junctions are fabricated using techniques borrowed from the semiconductor industry, but the materials and processes are entirely different from those used to make conventional electronics. This separation means that quantum computers and classical computers must be built in different facilities using different supply chains with different quality control standards. The gallium-doped germanium breakthrough changes this equation entirely. For the first time, we have a material that can function as both a conventional semiconductor and a superconductor, depending on how it's configured. This dual nature means that quantum and classical components can be fabricated on the same wafer, in the same facility, using the same trillion-dollar infrastructure that currently produces the processors in your laptop and smartphone. The implications of this compatibility extend far beyond manufacturing convenience. When you can integrate quantum and classical components at the atomic level, you create new possibilities for hybrid architectures that were previously impossible. Imagine a processor where quantum calculations occur alongside classical control circuits, where the delicate quantum states are protected by robust classical error correction systems, where the boundary between quantum and classical computation becomes fluid rather than absolute. But perhaps the most significant advantage of this approach lies in how it addresses the decoherence problem. The molecular beam epitaxy process creates crystals with extraordinary structural perfection. The spacing between atoms remains essentially unchanged from pure germanium, with only slight adjustments to accommodate the larger gallium atoms. This level of order reduces the random fluctuations and defects that cause quantum states to decohere. It's like the difference between trying to maintain your balance on a perfectly smooth floor versus a rocky, uneven surface. As you listen to this, quantum fields are fluctuating around you, through you, in the spaces between the atoms that make up your body. These aren't abstract mathematical constructs, but real physical phenomena that underlie the stability of matter itself. The electrons in the atoms of your skin are constantly exchanging virtual photons with the electromagnetic field. The quarks in your atomic nuclei are held together by the strong force, mediated by particles called gluons. Even empty space isn't truly empty, but filled with quantum fluctuations that give rise to measurable effects. This quantum reality becomes technologically relevant when we learn to control it with sufficient precision. Superconductivity itself is a quantum phenomenon that emerges when electrons form pairs that can flow through a material without resistance. These electron pairs, called Cooper pairs, behave as a single quantum entity that can maintain coherence across macroscopic distances. It's a bridge between the quantum and classical worlds, a way for quantum effects to manifest at scales we can see and manipulate. The challenge has always been creating the conditions for superconductivity to emerge reliably and controllably. Traditional superconductors require extremely low temperatures because thermal vibrations easily break apart the delicate Cooper pairs. The gallium-doped germanium system operates at 3.5 Kelvin, which is cold but achievable with standard laboratory refrigeration systems. More importantly, the superconducting properties can be turned on and off by applying electrical fields, creating the possibility for dynamic control of quantum states. This controllability opens up entirely new approaches to quantum computing. Instead of trying to isolate qubits from their environment, we might be able to engineer environments that naturally protect quantum coherence. Instead of fighting decoherence with complex error correction schemes, we might be able to prevent it from occurring in the first place. It's the difference between trying to keep a candle lit in a windstorm versus building a lantern that protects the flame. The theoretical framework for understanding these possibilities comes from decades of research into quantum many-body systems. When you have millions of atoms arranged in perfect crystalline order, their collective behavior can exhibit properties that none of them possess individually. Superconductivity is one example of this emergent quantum behavior, but there are others. Some materials exhibit quantum spin liquids, where magnetic moments remain in constant flux without ever settling into a fixed pattern. Others show topological order, where information is encoded in global properties that are inherently protected from local disturbances. The transition from laboratory curiosity to technological reality requires more than just scientific understanding. It demands engineering solutions that can be scaled, manufactured reliably, and integrated into systems that work in the real world. This is where the semiconductor industry's decades of accumulated expertise become invaluable. Consider what it takes to manufacture a modern processor. Silicon wafers must be polished to atomic smoothness. Features smaller than 10 nanometers must be etched with precision measured in fractions of an atom. Billions of transistors must function identically, with failure rates measured in parts per billion. This level of manufacturing sophistication didn't emerge overnight. It's the result of 60 years of continuous improvement, driven by relentless economic pressure to make computers faster, smaller, and more affordable. The gallium-doped germanium breakthrough allows quantum computing to leverage this entire manufacturing ecosystem. The same facilities that produce conventional semiconductors can now produce quantum processors. The same quality control systems that ensure the reliability of classical computers can be applied to quantum systems. The same economies of scale that drove down the cost of conventional computing can now work their magic on quantum technologies. This convergence is already beginning to happen. Research groups around the world have demonstrated that quantum processors can be manufactured in commercial semiconductor foundries without losing their quantum properties. Companies like Dirac have shown that silicon-based quantum chips can maintain world-class accuracy even when mass-produced, achieving over 99% fidelity in 2-qubit operations. The yield rates, a crucial metric for commercial viability, are approaching those required for profitable production. But the real revolution lies not just in manufacturing quantum computers more efficiently, but in manufacturing them at unprecedented scales. Traditional approaches to quantum computing are fundamentally limited by the need for individual control of each qubit. As you scale up to millions of qubits, the classical control systems become overwhelmingly complex. You need individual laser pulses or microwave signals for each qubit, individual readout systems for each measurement, individual error correction for each quantum operation. The semiconductor approach changes this scaling equation entirely. When qubits are integrated into the same substrate as their control electronics, when quantum operations can be controlled by electrical fields applied through conventional transistors, when error correction can be implemented in hardware rather than software, the scaling challenges become much more manageable. Instead of building larger and more complex control systems, you can integrate the control directly into the quantum processor itself. As we move deeper into 2025, something remarkable is happening across the quantum computing landscape. The fundamental challenges that once seemed insurmountable are yielding to sustained engineering effort. The physics problems that required breakthrough discoveries are becoming engineering problems that can be solved through systematic development. IBM has announced plans for fault-tolerant quantum computers by 2029. IonQ projects systems with 80,000 logical qubits by 2030. Google's recent demonstration of exponential error correction with their Willow processor shows that quantum computers can become more reliable as they grow larger, not less. These aren't wishful projections, but detailed roadmaps based on demonstrated technical milestones. The investment flowing into quantum technologies reflects this growing confidence. In the first 9 months of 2025 alone, quantum computing companies raised nearly $4 billion in equity funding, almost triple the amount raised in all of 2024. China has announced a national venture fund of over $130 billion for quantum and other emerging technologies. The European Union, the United States, and other nations are treating quantum computing as a strategic national priority. This convergence of scientific breakthrough, engineering progress, and economic investment suggests that we're approaching an inflection point. The transition from laboratory prototypes to commercial products, from scientific curiosity to practical technology, from quantum supremacy in artificial problems to quantum advantage in real applications. But perhaps the most intriguing aspect of this transition is how it might change our relationship with computation itself. Classical computers process information sequentially, breaking complex problems down into simple logical operations that can be performed one after another. Quantum computers approach problems holistically, exploring multiple solution paths simultaneously and converging on answers through interference and entanglement. This difference isn't just technical, it's almost philosophical. Classical computation mirrors the way we consciously think, step by step, building up solutions through logical progression. Quantum computation is more like intuition, where understanding emerges from the interaction of multiple possibilities that we can't directly observe or control. If you enjoy drifting through these explorations without interruption, members get every episode 48 hours early, completely ad-free. You can join them whenever you feel ready. The journey we're taking together doesn't depend on membership, but for those who find peace in uninterrupted contemplation, the option is there. The implications of ubiquitous quantum computing extend far beyond faster calculations or more efficient algorithms. When quantum processors become as common as classical ones, when quantum sensing becomes as routine as GPS, when quantum communication networks span the globe, we enter a world where the strange properties of quantum mechanics become part of the fabric of daily life. Consider quantum sensing, where the same principles that make quantum computing possible can be used to measure physical phenomena with unprecedented precision. Quantum magnetometers can detect magnetic fields billions of times weaker than those measured by conventional instruments. Quantum accelerometers can sense motion with accuracy that makes GPS seem crude by comparison. Quantum clocks can measure time with precision that reveals the gravitational effects of moving a few centimeters higher or lower in Earth's gravity well. These capabilities aren't just improvements in existing technologies, they enable entirely new applications. Medical imaging systems that can detect individual molecules within living cells. Navigation systems that work underground or underwater, where GPS signals can't reach. Geological surveys that can map underground resources or detect seismic activity with extraordinary sensitivity. The gallium-doped germanium breakthrough makes these applications more practical because it enables quantum sensors to be integrated directly into conventional electronic systems. Instead of requiring specialized facilities and expert operators, quantum sensing could become as routine as taking a photograph. The same smartphones that currently contain accelerometers, magnetometers, and GPS receivers might one day include quantum sensors that provide vastly superior capabilities. But the deeper transformation lies in how quantum technologies might change our understanding of information itself. In classical physics, information is abstract, something that exists independently of the physical system that stores or processes it. A bit of classical information is the same whether it's stored as a magnetic field on a hard drive, an electrical charge in memory, or marks on paper. Quantum information is fundamentally different. It cannot be copied perfectly due to the no-cloning theorem. It cannot be observed without being changed. It exists in superposition states that have no classical analogue. These properties, which seem like limitations, are actually the source of quantum computing's power. They're what enable quantum computers to explore multiple solution paths simultaneously, what allow quantum cryptography to detect eavesdropping with mathematical certainty, what make quantum communication networks fundamentally more secure than anything possible with classical technology. As quantum processors become more sophisticated and more widely deployed, they create the foundation for something even more transformative, a global quantum internet. This isn't simply a faster version of the current internet, but a fundamentally different kind of communication network based on quantum entanglement rather than classical information transfer. In a quantum network, information isn't transmitted from one point to another in the conventional sense. Instead, quantum states are shared between distant locations through entanglement, creating correlations that exist independently of the space between them. When two quantum systems are entangled, measuring one instantly determines the state of the other, regardless of the distance separating them. This isn't communication in the classical sense because no information actually travels between the locations, but it enables new forms of distributed computation and absolutely secure communication. The practical implementation of quantum networks requires the same kind of integration between quantum and classical systems that the gallium-doped germanium breakthrough enables. Quantum information must be generated, manipulated, stored, and transmitted using devices that can be manufactured reliably and operated routinely. The exotic physics must be packaged into systems that work in the real world, outside of carefully controlled laboratory environments. Early demonstrations of quantum networking are already happening on existing fiber optic infrastructure. Researchers have shown that quantum communication protocols can coexist with classical internet traffic on the same optical fibers. The challenge is scaling these demonstrations from laboratory curiosities to commercial technologies that can support millions of users across global distances. The implications of a mature quantum internet extend into realms we're only beginning to imagine. Distributed quantum computing, where problems are solved collaboratively by quantum processors located around the world. Quantum-enhanced sensing networks that can detect global phenomena by correlating measurements across vast distances. Communication systems that are secure not just against current threats, but against any possible future attack, even by adversaries with unlimited computational resources. But perhaps most intriguingly, a quantum internet might change our understanding of locality itself. In classical physics, objects have definite locations and interact only with their immediate neighbours. Information propagates from place to place at finite speeds, creating clear causal relationships between events. Quantum entanglement challenges this picture by creating correlations that are non-local, existing independently of space and time. When these non-local correlations become technologically useful, when they become part of the infrastructure of communication and computation, we enter a world where the boundaries between here and there, now and then, become more fluid. Not in any mystical sense, but in the precise, measurable way that quantum mechanics allows. Take a breath and consider how this quantum future might feel from the inside. Your device is connected not just by electromagnetic signals propagating through space, but by quantum correlations that exist outside the normal flow of time and causation. Information that exists in superposition until the moment you need it, then crystallizes into exactly the answer you are seeking. Computations that explore not just what is, but what might be, returning with insights drawn from the entire landscape of possibility. This is the world that the gallium-doped germanium breakthrough is quietly making possible. Not through dramatic revolution, but through the patient engineering of materials that can bridge the gap between quantum possibility and practical reality. The future is being built one atomic layer at a time, in the controlled environments of molecular beam epitaxy chambers, where the strange becomes routine and the impossible becomes inevitable. The story we're telling here is still unfolding, still being written in laboratories and fabrication facilities around the world, but the trajectory is becoming clear. The quantum age isn't arriving with fanfare or sudden transformation. It's emerging gradually, systematically, as the accumulated understanding of decades of research crystallizes into technologies that work reliably in the real world. And at the heart of this emergence lies a simple but profound insight, that the materials we use to build our technologies aren't just passive substrates for our devices, but active participants in determining what's possible. By engineering materials With the right properties at the atomic level, we can create conditions where the strange laws of quantum mechanics become practical tools for computation, communication, and sensing. The semiconductor breakthrough we've explored tonight is just one example of this materials-driven approach to quantum technologies, but it's a particularly significant one because it demonstrates that quantum and classical technologies don't have to exist in separate worlds. They can be integrated, unified, made to work together in ways that amplify the capabilities of both. As we continue this journey together in our next exploration, we'll delve deeper into the specific ways these quantum technologies are reshaping our understanding of reality itself, and how the merger of quantum mechanics with practical engineering is opening doors to possibilities we're only beginning to imagine. Close your eyes for a moment and picture waves meeting on the surface of a still pond. When two ripples encounter each other, they don't simply bounce off or pass through unchanged. Instead, they interfere, creating patterns of reinforcement and cancellation that are more complex and beautiful than either wave alone. This interference, this delicate interplay between possibility and reality, lies at the heart of every quantum calculation that will soon be humming quietly in the devices around you. The gallium-doped germanium breakthrough we've been exploring doesn't just solve manufacturing problems. It creates conditions where quantum interference can persist longer, remain more stable, and be controlled with unprecedented precision. Think of it as building a concert hall with perfect acoustics, where every note rings true, and every harmony emerges exactly as intended. The crystalline perfection achieved through molecular beam epitaxy creates an environment where quantum waves can interfere constructively, building towards solutions rather than dissolving into noise. This stability matters because quantum computing is fundamentally about orchestrating interference patterns. When a quantum computer calculates, it's not processing information step by step like a classical computer. Instead, it's setting up conditions where all possible answers exist simultaneously in superposition, then allowing them to interfere with each other until only the correct solution remains amplified, while incorrect possibilities cancel out. Imagine trying to find your way through a vast maze with infinite pathways. A classical computer would explore each route sequentially, methodically checking every possibility until it found the exit. A quantum computer explores all paths simultaneously, but arranges the exploration so that paths leading nowhere interfere destructively and fade away, while the path to the solution grows stronger and brighter through constructive interference. This process requires extraordinary precision. The quantum waves representing different solution paths must maintain their coherence long enough for the interference patterns to develop. They must be isolated from environmental disturbances that could destroy the delicate phase relationships. And the final measurement must capture the interference pattern at exactly the right moment, when the correct answer has been amplified and the incorrect ones have been suppressed. The new semiconductor superconductors make this orchestration possible at scales previously unimaginable. When quantum interference can be controlled with the same precision, tools used to manufacture microprocessors, when millions of qubits can maintain coherence simultaneously, when error rates drop to levels where quantum calculations become reliable rather than probabilistic, we cross a threshold into computational capabilities that transcend anything possible with classical physics. As you listen to these words, your brain is performing calculations that no classical computer could replicate. Not because your neurons are faster than silicon transistors, but because biological systems naturally exploit quantum mechanical effects in ways we're only beginning to understand. The efficiency of photosynthesis, the sensitivity of bird navigation, even the binding of oxygen to hemoglobin in your blood, all involve quantum processes that classical physics cannot fully explain. This suggests something profound about the relationship between quantum mechanics and the emergence of complexity in our universe. The same quantum effects that make quantum computing possible also seem to be essential for the biochemical processes that sustain life itself. It's as if the universe has been running quantum calculations since the beginning of time, and we're only now learning to read the code. The topology of quantum systems, the way quantum information is structured and protected, offers insights into why this might be so. In mathematics, topology studies properties that remain unchanged under continuous deformations. A coffee cup and a donut have the same topology because you can smoothly transform one into the other without tearing or cutting. Similarly, topological quantum states possess properties that remain stable even when the system is disturbed by noise or imperfections. This topological protection is what Microsoft has been pursuing with their approach to quantum computing. By encoding quantum information in topological properties rather than in individual particles, they create qubits that are inherently protected against the kinds of local disturbances that cause decoherence in other systems. It's like storing information in the global structure of a knot rather than in the position of a particular strand. But the gallium-doped germanium breakthrough opens new possibilities for creating topological quantum states in semiconductor systems. When superconducting regions can be patterned with nanometer precision alongside semiconducting areas, when the interfaces between these regions can be controlled at the atomic level, it becomes possible to engineer artificial materials with topological properties that don't exist in nature. These artificial topological materials could host quantum states that are protected not by careful isolation from the environment, but by the fundamental mathematical structure of the system itself. Imagine quantum information that heals itself when damaged, that remains coherent even in the presence of noise and fluctuations, that scales up naturally without requiring exponentially complex error correction schemes. Take a moment to consider what this might mean for the long-term evolution of intelligence in our universe. If topologically protected quantum computation is a natural feature of matter under the right conditions, then the emergence of quantum technologies might represent not just a technological breakthrough, but a kind of phase transition in the organization of information itself. There's something deeply mysterious about the act of measurement in quantum mechanics that even a century of scientific progress hasn't fully resolved. Before measurement, a quantum system exists in superposition, embodying all possible states simultaneously. But the moment we observe it, this superposition collapses into a single definite outcome. What causes this collapse? When exactly does it occur? And why do we never observe superposition states directly in our everyday experience? These questions, collectively known as the measurement problem, have puzzled physicists and philosophers since the early days of quantum theory. They're not just academic curiosities, but practical challenges that must be addressed as quantum technologies become more sophisticated and more widely deployed. The traditional approach to quantum measurement requires coupling the quantum system to a classical measurement apparatus. This coupling inevitably disturbs the quantum state, causing decoherence and collapse. But the boundary between quantum and classical is not absolute. As measurement devices become more sensitive and more sophisticated, they begin to exhibit quantum properties themselves. The integration of quantum and classical components, enabled by semiconductor superconductors, blurs this boundary in fascinating ways. When quantum processors and classical control systems are fabricated on the same substrate, when the measurement apparatus itself can be placed in superposition, the traditional distinction between observer and observed becomes more fluid. This opens up possibilities for new kinds of quantum measurements that don't necessarily collapse the quantum state. Weak measurements, quantum non-demolition measurements, and other exotic protocols that allow us to extract information from quantum systems without fully destroying their quantum properties. These techniques could enable quantum computers to perform calculations that are partially observed and corrected in real time, without losing the quantum advantage. But perhaps more intriguingly, they might allow us to study the measurement process itself with unprecedented precision. By creating systems where the boundary between quantum and classical can be controlled and manipulated, we might finally be able to understand what actually happens when a quantum superposition becomes a classical outcome. As you contemplate this boundary between the quantum and classical worlds, notice how it mirrors other boundaries in your own experience. The transition from sleeping to waking, from unconscious to conscious processing, from possibility to actuality. These transitions happen countless times each day, yet their fundamental nature remains as mysterious as quantum measurement itself. The transformation of quantum computing from laboratory curiosity to commercial technology is being driven not just by scientific breakthroughs, but by economic forces that are reshaping entire industries. The potential advantages of quantum computation are so significant that they're attracting investment levels typically reserved for oil exploration or pharmaceutical development. Consider the scale of problems that quantum computers might eventually solve. Optimizing the logistics networks that deliver goods around the world, designing new materials with properties tailored for specific applications, simulating molecular interactions to discover new medicines, breaking the cryptographic codes that protect digital communications while simultaneously creating new forms of unbreakable encryption. Each of these applications represents not just technological advancement, but economic value measured in trillions of dollars. The company that first achieves practical quantum advantage in drug discovery could revolutionize medicine. The nation that deploys quantum-enhanced artificial intelligence could gain decisive strategic advantages. The financial institutions that master quantum optimization could reshape global markets. This economic pressure is accelerating development in ways that pure scientific curiosity never could. When billions of dollars are at stake, when national competitiveness hangs in the balance, when first-mover advantages could persist for decades, the resources devoted to solving technical challenges expand exponentially. The semiconductor superconductor breakthrough is particularly significant because it addresses the economic as well as the technical barriers to quantum computing. Manufacturing costs that seemed prohibitive when quantum processors required entirely separate fabrication facilities become manageable when they can leverage existing semiconductor infrastructure. Quality control standards that seemed impossible to achieve with exotic materials become routine when the same processes used to manufacture classical processors can be applied to quantum systems. But the deeper economic transformation lies in how quantum technologies might change the nature of computation itself. Classical computers process information by manipulating bits sequentially, requiring time and energy proportional to the complexity of the calculation. Quantum computers can, in principle, solve certain problems exponentially faster, using resources that scale much more favorably with problem size. This difference isn't just about speed, it's about the fundamental relationship between information processing and physical resources. In a world where quantum computers are commonplace, problems that currently require massive data centers and enormous energy consumption might be solved by devices no larger than today's smartphones. There's a tempting symmetry between the mysteries of quantum mechanics and the mysteries of consciousness that has captured imaginations since the early days of quantum theory. Both involve phenomena that seem to resist classical explanation. Both involve observers and observations in fundamental ways. Both suggest that reality might be more fluid and more dependent on information than our everyday experience suggests. Some interpretations of quantum mechanics, though they remain highly speculative and lack scientific consensus, propose that consciousness might play a role in the collapse of quantum wave functions. The idea is that conscious observation somehow selects which of many possible outcomes becomes real. This interpretation remains controversial and unproven, with most physicists favouring explanations that don't require conscious observers to play a special role in physical processes. Yet the parallels are intriguing, even if they don't constitute scientific evidence for any particular theory of consciousness. Both quantum systems and conscious experiences seem to involve the emergence of definite states from underlying possibilities. Both involve correlations and entanglements that transcend simple mechanical explanations. Both suggest that information and observation might be more fundamental than matter and energy. The development of quantum technologies might shed new light on these parallels, not by proving that consciousness is quantum mechanical, but by giving us better tools for understanding the relationship between information and physical reality. When quantum computers become sophisticated enough to simulate biological systems with quantum accuracy, we might be able to study the role that quantum effects play in neural processing. Some researchers have proposed that quantum coherence in microtubules within neurons might be involved in consciousness, though this remains a highly speculative hypothesis without strong empirical support. Others suggest that quantum effects in ion channels or other cellular structures might influence neural computation in subtle but important ways. These ideas are far from proven, but they illustrate how quantum technologies might eventually help us understand the physical basis of consciousness. What seems more certain is that as we learn to control and manipulate quantum systems with greater precision, we develop new conceptual tools for thinking about information, observation, and the emergence of classical reality from quantum possibilities. These tools might prove useful for understanding consciousness, even if consciousness itself doesn't turn out to be fundamentally quantum mechanical. As quantum technologies transition from research laboratories to commercial deployment, they bring with them ethical challenges that we're only beginning to recognize and address. The same capabilities that make quantum computers so powerful also make them potentially dangerous in the wrong hands. Quantum computers capable of breaking current cryptographic systems could undermine the privacy protections that secure everything from banking transactions to personal communications. The timeline for this threat is uncertain, but the consequences could be profound. Entire industries built on the assumption that certain mathematical problems are practically unsolvable might find their foundations suddenly shifted. This has sparked a race to develop quantum-resistant cryptography, new mathematical approaches to encryption that remain secure even against quantum attacks. But the transition to post-quantum cryptography is itself a massive undertaking, requiring coordination across industries and governments to ensure that critical systems remain protected. The advantages that quantum technologies provide in optimization and simulation could also create new forms of inequality. Nations or corporations with access to quantum computers might gain decisive advantages in everything from financial markets to materials science. The gap between quantum haves and have-nots could become more significant than any previous technological divide. But quantum technologies also offer unprecedented opportunities for solving problems that affect all of humanity. Climate modeling with quantum accuracy could help us understand and address environmental challenges with greater precision. Quantum-enhanced drug discovery could accelerate the development of treatments for diseases that affect billions of people. Quantum communication networks could provide secure communications for dissidents and democracy advocates in authoritarian regimes. The key is ensuring that the development and deployment of quantum technologies serves broad human interests rather than narrow competitive advantages. This requires international cooperation, ethical guidelines, and governance structures that can evolve as quickly as the technology itself. As you reflect on these possibilities, consider how they might touch your own life. The quantum revolution isn't just about abstract computational advantages or geopolitical strategies. It's about the tools we'll use to understand our world, the security of our communications, the effectiveness of our medicines, and the sustainability of our civilization. The story we've been exploring tonight represents just one thread in a larger tapestry of technological convergence that's reshaping our world. Artificial intelligence systems are becoming more sophisticated and more capable. Biotechnology is giving us unprecedented control over biological processes. Nanotechnology is enabling us to manipulate matter at the atomic scale, and quantum technologies are opening up entirely new computational and sensing capabilities. Each of these technological domains is advancing rapidly on its own, but their true potential might emerge from their intersection. Quantum-enhanced artificial intelligence could solve problems that neither classical AI nor quantum computing could address alone. Quantum sensors could monitor biological processes with precision that enables new forms of medical intervention. Quantum communication could provide the security infrastructure needed for advanced biotechnology applications. The gallium-doped germanium breakthrough is significant not just because it advances quantum computing, but because it demonstrates how fundamental materials science research can suddenly accelerate progress across multiple technological domains simultaneously. When new materials with unprecedented properties become available, they create opportunities that couldn't be anticipated from theoretical studies alone. This suggests that we might be approaching a period of accelerating technological convergence, where advances in one field rapidly enable breakthroughs in others. The timescales for technological development could compress as different technologies amplify each other's capabilities. But convergence also brings complexity. Systems that integrate quantum, classical, biological, and artificial components will be more powerful, but also more difficult to understand and control. The unintended consequences of such systems could be more significant and more difficult to predict. This is why the patient, methodical approach exemplified by the molecular beam epitaxy research is so important. Each atomic layer deposited with precision, each measurement carefully validated, each result rigorously tested before moving to the next step. This methodical approach provides a foundation of understanding that can support the more complex systems to come. As we near the end of our journey together tonight, let's step back and consider this quantum revolution from the perspective of deep time. The universe has been performing quantum calculations since its beginning. The quantum fluctuations in the early cosmos seeded the large-scale structure we observe today. The quantum processes in stellar cores forge the elements that make planets and life possible. The quantum mechanics of molecular bonds enables the chemistry of life itself. From this perspective, the development of quantum technologies represents not the invention of something entirely new, but the recognition and technological harnessing of processes that have been operating throughout cosmic history. We're learning to read a language that the universe has been speaking all along. This recognition brings with it a sense of continuity and connection that transcends the immediate practical applications of quantum computing. We're not separate from the quantum processes we're learning to control. We are expressions of those processes, temporary patterns in the same quantum fields that we're now learning to manipulate technologically. The material science breakthroughs that enable practical quantum computing are themselves expressions of our growing understanding of how quantum mechanics shapes the properties of matter. Each advance in our ability to control quantum systems at the atomic level brings us closer to understanding our own place in the quantum cosmos. This understanding might ultimately prove more valuable than any particular technological application. As we develop more sophisticated quantum technologies, as we learn to think more naturally in quantum terms, as we begin to see classical reality as an emergent property of underlying quantum processes, our entire worldview shifts. The boundaries between observer and observed, between mind and matter, between possibility and actuality become more fluid. Not because quantum mechanics directly supports any particular philosophical position, but because it forces us to question assumptions about reality that seemed unquestionable from a purely classical perspective. Take one final breath and imagine what it might feel like to live in a fully quantum-enabled world. Your devices connected not just by electromagnetic signals, but by quantum entanglement. Your medicine designed through quantum simulation of molecular interactions. Your communication secured by the fundamental laws of physics, rather than mathematical complexity. More subtly, imagine thinking in quantum terms as naturally as you now think in classical ones. Comfortable with uncertainty and superposition. Appreciating the role of observation in shaping reality. Understanding that possibilities can be as real and as important as actualities. This is the world that the semiconductor superconductor breakthrough is quietly making possible. Not through dramatic revolution, but through the patient accumulation of knowledge and capability. Not by overthrowing the classical world, but by revealing the quantum processes that underlie it. The revolution is happening now, in laboratories around the world, one atomic layer at a time. And while the full implications won't be clear for decades to come, the trajectory is unmistakable. We're entering an age where the strange becomes familiar, where the impossible becomes routine, where the quantum nature of reality becomes a technological resource rather than a philosophical puzzle. The future is quantum, and it's arriving more quietly, more steadily, and more inevitably than most of us realise. If you found yourself wondering about the deeper connections between consciousness and the quantum realm, you might enjoy exploring another fascinating question. Could quantum entanglement be the hidden science behind manifestation? It's a journey that takes us even further into the mysterious territory where physics meets philosophy, where possibility becomes reality, and where the boundaries of what we think we know begin to shimmer and shift. Until our paths cross again in the vast landscape of knowledge, keep wondering, keep questioning, and remember that in a quantum universe, even the act of observation changes what's possible. As the night deepens around you, let's venture into territory where the boundaries between the physical and the profound begin to dissolve. The semiconductor breakthrough we've been exploring doesn't just represent an engineering triumph. It hints at something far more fundamental about the nature of reality itself. When we can manufacture materials that bridge the quantum and classical worlds with atomic precision, we're not just building better computers, we're creating windows into the deepest layers of existence. Consider the implications of what we've discovered. Matter, at its most fundamental level, doesn't behave according to the solid, predictable rules of our everyday experience. Instead, it exists in a realm of possibility and probability, where particles can be in multiple places simultaneously, where information can be shared instantaneously across vast distances, where the very act of observation seems to shape what becomes real. The gallium-doped germanium breakthrough allows us to harness these quantum properties not as curiosities confined to laboratory experiments, but as practical tools that can be manufactured and deployed at scale. This suggests something profound about the relationship between consciousness and cosmos, between observation and reality, between what we think we know and what might actually be possible. Take a moment to notice your breathing, in and out, steady and rhythmic. Now consider that this simple biological process involves quantum mechanical effects at every step. The binding of oxygen to hemoglobin in your bloodstream depends on quantum tunneling. The enzymatic reactions that extract energy from glucose rely on quantum coherence effects. Even the neural processes that allow you to be aware of your breathing involve quantum mechanics at the molecular level. You are not separate from the quantum realm we've been exploring. You are an expression of it, a temporary pattern of quantum fields organized in such a way that the universe can observe itself through your consciousness. The same quantum principles that enable superconducting qubits to maintain coherence enable your neurons to process information. The same quantum entanglement that promises revolutionary computing capabilities might play a role in the binding of conscious experience itself. This isn't to suggest that consciousness is merely a quantum computer, though some interpretations remain open to this possibility. Rather, it's to recognize that the quantum nature of reality isn't confined to physics laboratories or exotic technologies. It's the substrate upon which all experience, all life, all awareness emerges. There's something almost mystical about the mathematical precision with which quantum mechanics describes the behavior of matter and energy. The equations that govern quantum systems don't just predict outcomes. They seem to encode the fundamental logic of reality itself. When physicists write down the Schrödinger equation or calculate the properties of quantum fields, they're not just modeling physical phenomena. They're discovering the mathematical language that the universe speaks. The fact that this mathematical language can be translated into practical technologies, that abstract equations about probability, amplitudes, and wave function collapse can guide the fabrication of materials with unprecedented properties, suggest a deep connection between mathematical truth and physical reality. It's as if the universe is not just mathematically describable, but mathematically constituted. This perspective, sometimes called mathematical Platonism, proposes that mathematical structures exist independently of physical reality, and that what we call the physical universe is actually an expression of underlying mathematical relationships. From this view, the semiconductor-superconductor breakthrough represents not just the discovery of new materials, but the uncovering of mathematical truths that were waiting to be found. Consider the elegance of molecular beam epitaxy, where atoms are deposited one layer at a time with precision measured in fractions of a nanometer. This process doesn't just happen to work because we've become clever engineers. It works because the mathematical relationships that govern atomic bonding, crystalline structure, and quantum coherence create possibilities that we're learning to read and exploit. The success of quantum technologies suggests that reality is not fundamentally chaotic or random, despite the probabilistic nature of quantum mechanics. Instead, it's structured according to principles that can be understood, predicted, and harnessed. The randomness we observe at the quantum level gives way to elegant patterns and relationships when viewed from the proper mathematical perspective. As you contemplate this mathematical substrate of reality, notice how it mirrors your own experience of understanding. When you suddenly grasp a complex idea, when disparate pieces of information suddenly click into place, when the solution to a problem appears with crystalline clarity, you're experiencing something analogous to the way quantum systems collapse from superposition into definite states. The process of understanding itself might be quantum mechanical in nature, involving the constructive interference of multiple possibilities until a single coherent interpretation emerges. This remains speculative, with no scientific consensus, but the parallels are intriguing. Both understanding and quantum measurement involve the emergence of definiteness from indefiniteness, the crystallization of possibility into actuality. In the emerging quantum technological landscape, information begins to behave less like static data and more like a living ecosystem. Classical information can be copied perfectly, transmitted without loss, and stored indefinitely. Quantum information, by contrast, exists in delicate relationships with its environment. It cannot be cloned, cannot be observed without being changed, and exhibits correlations that transcend the boundaries of space and time. This difference isn't just technical, it suggests a fundamentally different relationship between information and reality. Classical information describes the world from the outside, like a map that represents territory without being part of it. Quantum information is embedded in the world, inseparable from the physical processes that store and manipulate it. The semiconductor-superconductor breakthrough enables us to create environments where quantum information can flourish. The crystalline perfection achieved through molecular beam epitaxy provides a kind of protected habitat for quantum states, allowing them to maintain their delicate coherence for extended periods. It's ecosystem engineering at the atomic level, creating conditions where quantum information can evolve and interact according to its natural laws. But the implications extend beyond quantum computing. As quantum technologies become more sophisticated, as quantum networks begin to span global distances, as quantum sensing becomes ubiquitous, we might find ourselves living within an information ecosystem that operates according to quantum rather than classical principles. Imagine a world where information exists not just as data to be processed, but as a fundamental constituent of reality itself, where the boundaries between information and matter, between software and hardware, between mind and world, become increasingly fluid, where the act of observation doesn't just reveal information, but participates in its creation. This vision remains largely speculative, but it's grounded in the mathematical structure of quantum mechanics and the practical capabilities that quantum technologies are beginning to demonstrate. As we learn to manipulate quantum information with greater precision and at larger scales, we're not just building better tools, we're discovering new forms of relationship between consciousness and cosmos. Take a breath and consider how this might already be true in your own experience. The thoughts you're thinking as you listen to these words, the memories you're accessing, the connections you're making between ideas, all involve information processing in biological systems that operate according to quantum mechanical principles at the molecular level. You are already part of a quantum information ecosystem. The question isn't whether such ecosystems exist, but whether we'll learn to recognize and work with them consciously rather than unconsciously. Even as we develop increasingly sophisticated quantum technologies, even as we learn to control and manipulate quantum systems with unprecedented precision, the fundamental mystery of quantum mechanics remains intact. We can predict the behavior of quantum systems with extraordinary accuracy, but we still don't fully understand why they behave the way they do. The measurement problem, the role of consciousness in observation, the nature of quantum reality before measurement, the mechanism of wave function collapse. These questions remain as puzzling today as they were a century ago when quantum mechanics was first formulated. Our technological mastery has far outpaced our conceptual understanding. This persistence of mystery isn't a failure of science. It's a reminder that reality is deeper and stranger than any theoretical framework we've yet developed to describe it. The quantum technologies we're building work not because we've solved all the conceptual puzzles, but because we've learned to work with the mystery rather than against it. The semiconductor superconductor breakthrough exemplifies this approach. Researchers didn't need to understand everything about superconductivity or quantum coherence to create materials that exhibit these properties. They needed to understand enough to control the relevant variables, to create the right conditions, to guide the natural tendencies of quantum systems toward useful outcomes. This suggests a different relationship with knowledge than the one that dominated science for centuries. Instead of seeking complete understanding before acting, we learn to act skillfully within the bounds of partial knowledge. Instead of demanding certainty before proceeding, we develop comfort with probability and possibility. This shift in epistemological approach might be one of the most significant implications of the quantum revolution. As quantum thinking permeates other fields, as quantum metaphors become part of common discourse, as quantum technologies become part of everyday experience, we might find ourselves becoming more comfortable with uncertainty, more appreciative of paradox, more open to multiple simultaneous possibilities. Notice how this might already be changing your own relationship with knowledge. The complex topics we've explored tonight, the interplay between technical precision and conceptual mystery, the way understanding emerges gradually rather than suddenly, all reflect a more quantum approach to learning. You don't need to understand everything about quantum mechanics to appreciate its implications. You don't need to resolve all the paradoxes to benefit from quantum technologies. You can live comfortably with questions that don't yet have answers, with possibilities that remain indefinite, with mysteries that enhance rather than diminish the richness of experience. There's a beautiful resonance between the scales at which quantum effects operate and the scales at which consciousness emerges. Both involve phenomena that can't be reduced to the simple sum of their parts. Both exhibit properties that emerge from complex interactions between many components. Both resist explanation in purely mechanical terms. The gallium-doped germanium breakthrough operates at the intersection of these scales. Individual atoms arranged with quantum precision create macroscopic properties that have no classical analogue. Millions of quantum interactions orchestrated by classical control systems give rise to computational capabilities that transcend anything possible with either quantum or classical systems alone. This resonance across scales suggests that the boundaries we draw between different levels of reality, between quantum and classical, between physical and mental, between individual and collective, might be more fluid than our conceptual frameworks suggest. The same principles that govern the behavior of electrons in superconducting materials might also govern the emergence of consciousness from neural networks, the formation of collective intelligence from individual minds, the crystallization of culture from social interactions. This isn't to claim that consciousness is literally quantum mechanical, though some interpretations remain open to this possibility. Rather, it's to recognize that the mathematical structures that describe quantum systems, the principles of emergence and self-organization, the role of information and observation, apply across multiple scales of natural organization. As you reflect on your own experience of consciousness, notice how it exhibits quantum-like properties. Your thoughts exist in superposition until the moment you articulate them. Your memories are probabilistic, influenced by the act of recall. Your sense of identity emerges from the interference patterns created by countless experiences, beliefs, and possibilities. The development of quantum technologies might give us new tools for understanding these parallels, not by reducing consciousness to quantum mechanics, but by revealing the deeper organizational principles that both domains share. As we learn to think more naturally in quantum terms, as we become comfortable with superposition and entanglement and emergence, we might discover new ways of understanding the nature of mind itself. The quantum revolution we've been exploring tonight is happening quietly, without fanfare or dramatic announcements. It's not arriving as a sudden disruption, but as a gradual transformation of the technological landscape. The semiconductor superconductor breakthrough exemplifies this gentle approach to revolutionary change. Instead of overthrowing existing manufacturing infrastructure, it leverages and enhances it. Instead of requiring entirely new scientific disciplines, it integrates insights from materials science, quantum physics, and electrical engineering. Instead of promising impossible solutions to all problems, it offers incremental improvements that compound over time into transformative capabilities. This gentleness might be one of the most important characteristics of the emerging quantum age. Rather than imposing quantum thinking on classical systems, rather than forcing quantum solutions to classical problems, the most successful approaches seem to involve finding natural interfaces between quantum and classical domains. The molecular beam epitaxy process that enables precise atomic control doesn't fight against the natural tendencies of matter. Instead, it creates conditions where atoms naturally arrange themselves into the desired configurations. The superconducting properties of gallium-doped germanium emerge spontaneously when the material is cooled below its critical temperature. The quantum coherence that enables quantum computation arises naturally from the mathematical structure of quantum mechanics. This suggests a different approach to technological development, one that works with natural principles rather than against them. Instead of brute force solutions that overcome natural limitations through sheer engineering effort, quantum technologies often succeed by aligning themselves with the inherent tendencies of physical systems. As you consider the implications of this approach, notice how it might apply to other domains of human activity. Instead of forcing solutions to complex problems, what would it mean to create conditions where solutions emerge naturally? Instead of imposing our will on systems we don't fully understand, how might we learn to work with their inherent intelligence? The quantum revolution isn't just changing our technological capabilities, it's teaching us new ways of relating to complexity, uncertainty, and emergence. It's showing us that the most powerful interventions are often the gentlest ones, that the most profound changes occur gradually rather than suddenly, that the most sustainable solutions work with natural principles rather than against them. As quantum technologies mature and proliferate, they create expanding circles of influence that extend far beyond their immediate applications. The semiconductor superconductor breakthrough doesn't just enable better quantum computers, it opens up new possibilities for quantum sensing, quantum communication, quantum materials design, and applications we haven't yet imagined. Each new capability creates opportunities for further innovation. Quantum sensors enable more precise measurements, which enable better understanding of natural phenomena, which enables new scientific discoveries, which enable new technologies. Quantum communication enables secure networks, which enable new forms of collaboration, which enable collective intelligence applications, which enable solutions to problems that no individual organization could address alone. This expanding circle of influence reflects a fundamental characteristic of information technologies. Unlike physical resources, which become depleted through use, information resources become more valuable as they're shared and combined. Quantum information exhibits this property even more dramatically than classical information, because quantum systems can exhibit correlations and entanglements that have no classical analogue. As quantum networks begin to span global distances, as quantum computers become accessible through cloud computing platforms, as quantum sensing becomes embedded in everyday devices, we might find ourselves participating in forms of collective intelligence that transcend the boundaries of individual minds and organizations. This possibility remains largely speculative, but it's grounded in the mathematical properties of quantum information and the trajectory of technological development. If quantum entanglement can create correlations between distant physical systems, if quantum computation can solve certain problems exponentially faster than classical methods, if quantum sensing can detect phenomena that are invisible to classical instruments, then quantum technologies might enable new forms of collective awareness and collective intelligence. Take a moment to imagine what this might feel like from the inside. Your device is connected not just to information networks, but to quantum correlation networks that enable forms of shared experience we can barely imagine. Your decisions informed not just by classical data processing, but by quantum computation that explores multiple possibilities simultaneously. Your awareness expanded not just through better information, but through quantum sensing that reveals hidden dimensions of reality. This vision remains far from current technological capabilities, but the trajectory is clear. Each advance in quantum technology opens up new possibilities for connection, correlation, and collective intelligence. The expanding circles of quantum influence might eventually encompass not just our technologies, but our consciousness itself. As we near the end of our exploration, it's worth asking a question that transcends technical capabilities and economic applications. What is the deeper purpose of developing quantum technologies? What are we really trying to achieve as we learn to harness the strange properties of quantum mechanics? One answer is purely practical. Quantum computers might solve problems that are beyond the reach of classical computation. Quantum sensors might detect phenomena that are invisible to classical instruments. Quantum communication might provide security that is guaranteed by the laws of physics rather than mathematical complexity. But there's another answer that's more philosophical. By learning to work with quantum systems, by developing technologies that operate according to quantum principles, by thinking more naturally in quantum terms, we're expanding our relationship with reality itself. We're learning to work with uncertainty rather than against it, to appreciate possibility as well as actuality, to recognize the role of observation in shaping what becomes real. This expanded relationship with reality might be the most significant outcome of the quantum revolution. Not just better technologies, but better ways of being in the world. Not just more powerful computation, but more nuanced understanding. Not just greater control over physical systems, but greater appreciation for the mystery and beauty of existence itself. The semiconductor superconductor breakthrough we've been exploring embodies this deeper purpose. It's not just about manufacturing better quantum computers, it's about creating materials that bridge the quantum and classical worlds, that make the strange familiar, that integrate the mysterious with the practical. As you reflect on your own purpose, your own relationship with reality, consider how quantum thinking might influence your approach to uncertainty, possibility, and observation. You don't need to become a quantum physicist to benefit from quantum perspectives. You can appreciate superposition in your own decision-making processes, recognize entanglement in your relationships with others, understand the role of observation in shaping your experience of reality. The quantum revolution isn't just changing our technologies, it's changing our consciousness, our understanding of what's possible, our relationship with the deepest principles that govern existence itself. We began this journey by considering how scientists had solved a puzzle that had frustrated quantum computing researchers for decades. We've travelled through the technical details of molecular beam epitaxy and superconducting semiconductors, through the implications for quantum computing and quantum sensing, through the philosophical questions that quantum technologies raise about the nature of reality itself. Now, as our exploration draws to a close, we find ourselves returning to where we started, but with deeper understanding. The breakthrough we've been discussing isn't just a technical achievement, it's a window into the quantum nature of reality that has been there all along, waiting for us to develop the tools and concepts necessary to recognize it. The gallium atoms substituted into the germanium crystal lattice create superconducting properties that emerge spontaneously when the material is cooled below its critical temperature. But these properties aren't imposed from the outside. They're inherent in the mathematical structure of the system, latent possibilities that become actual under the right conditions. This suggests something profound about the relationship between possibility and actuality, between the potential and the real. The quantum technologies we're developing don't create new physical laws. They reveal and harness laws that have been operating throughout the history of the universe. The same quantum principles that enable superconducting qubits to maintain coherence have been shaping the evolution of matter and energy since the Big Bang. The same quantum entanglement that promises revolutionary communication technologies connects every particle in the universe in an invisible web of correlation. The same quantum superposition that enables parallel computation has been exploring multiple possibilities simultaneously since the beginning of time. From this perspective, the development of quantum technologies represents not the invention of something entirely new, but the recognition of something eternal. We're learning to read a language that the universe has been speaking all along, to work with principles that have been operating since the first moments of cosmic evolution. As you settle into the quiet that follows our journey together, carry with you this sense of connection to the deeper principles that govern existence. You are not separate from the quantum processes we've been exploring. You are an expression of them, a temporary pattern in the eternal dance of possibility and actuality that creates and sustains the cosmos. The revolution we've been discussing is happening not just in laboratories and manufacturing facilities, but in consciousness itself. As we learn to think more naturally in quantum terms, as we become comfortable with uncertainty and possibility, as we recognize the role of observation in shaping reality, we participate in the ongoing evolution of intelligence in the universe. The future is quantum not because quantum technologies will replace classical ones, but because quantum thinking will transform our understanding of what's possible. The breakthrough we've explored tonight is just the beginning of a much larger transformation, one that will unfold over decades and centuries as we learn to work more skillfully with the mysterious principles that govern the deepest levels of reality. Until we meet again in the vast landscape of knowledge and wonder, remember that every breath you take, every thought you think, every moment of awareness you experience participates in the same quantum processes that enable superconducting qubits and quantum entanglement and all the other phenomena we've explored tonight. In the depths of fabrication facilities across the world, machines are humming with a precision that borders on the miraculous. They're depositing atoms one by one, layer by layer, building structures so small that millions could fit on the head of a pin. Yet these microscopic constructions are about to reshape industries worth trillions of dollars. What's remarkable isn't just the scale of this transformation, but how quietly it's happening. While headlines chase the latest artificial intelligence breakthrough or space exploration milestone, the real revolution is unfolding in clean rooms where the air itself is purer than anything you've ever breathed. The semiconductor superconductor materials we've been exploring don't just represent a single breakthrough. They're the foundation for an entire ecosystem of technologies that are beginning to emerge from research laboratories into commercial reality. Each advance in materials science creates new possibilities that ripple outward through multiple industries simultaneously. Consider the manufacturing challenge that seemed impossible just a few years ago. Creating quantum devices required exotic fabrication processes, specialized facilities, and materials that could only be produced in small quantities under carefully controlled laboratory conditions. The cost per device was measured in millions of dollars, and the failure rates were so high that most prototypes never functioned at all. Now, with gallium-doped germanium systems, that equation is changing dramatically. The same 300mm wafer fabrication facilities that produce conventional semiconductors can manufacture quantum processors. The same quality control systems that ensure the reliability of smartphone chips can be applied to quantum devices. The same supply chains that deliver billions of conventional processors each year can scale to support quantum technologies. This convergence of manufacturing capabilities is creating what engineers call a virtuous cycle. As production volumes increase, costs decrease. As costs decrease, new applications become economically viable. As new applications emerge, research and development investments increase. As investment increases, the pace of technological advancement accelerates. But the deeper transformation lies in how this convergence is changing the relationship between quantum and classical technologies. For decades, these two domains existed in parallel universes. Quantum physicists worked with exotic materials and cryogenic temperatures. Semiconductor engineers optimized silicon transistors and integrated circuits. The two communities rarely collaborated because their tools, techniques, and theoretical frameworks were fundamentally incompatible. The gallium-doped germanium breakthrough creates a bridge between these worlds. Suddenly, quantum engineers can leverage 60 years of accumulated expertise in semiconductor manufacturing. Classical circuit designers can incorporate quantum components into their architectures. Materials scientists can apply quantum mechanical insights to improve conventional semiconductors. Take a moment to appreciate what this convergence means for the pace of innovation. Instead of quantum technologies developing in isolation, advancing slowly through incremental laboratory improvements, they can now tap into the exponential scaling curves that have driven the semiconductor industry for decades. The same economic forces that made classical computers ubiquitous are now accelerating quantum development. As quantum processors become more sophisticated and more widely available, they enable applications that were previously confined to theoretical speculation. The improved coherence times and reduced error rates made possible by semiconductor superconductors are opening up entirely new categories of quantum algorithms and computational approaches. One of the most intriguing developments is the emergence of hybrid quantum classical algorithms that leverage the strengths of both computational paradigms. Classical computers excel at logical operations, data management, and sequential processing. Quantum computers excel at exploring multiple possibilities simultaneously, optimizing complex systems, and simulating quantum mechanical phenomena. When these capabilities can be integrated on the same chip, when quantum and classical components can share data without the delays and losses associated with external interfaces, entirely new computational architectures become possible. Algorithms that were impractical when quantum and classical processing occurred on separate systems suddenly become viable. The implications extend beyond pure computation into areas like machine learning and artificial intelligence. Classical neural networks process information through layers of interconnected nodes, adjusting connection strengths based on training data. Quantum neural networks can explore multiple training paths simultaneously, potentially discovering patterns and relationships that would be invisible to classical approaches. This isn't about replacing artificial intelligence with quantum intelligence, though some researchers are exploring that possibility. Rather, it's about creating hybrid systems where quantum processing handles the exploration of possibility space, while classical processing manages the implementation of discovered solutions. Early demonstrations of these hybrid approaches are already showing promising results. Quantum-enhanced optimization algorithms are finding better solutions to complex scheduling problems. Quantum machine learning models are identifying subtle patterns in data that classical models miss. Quantum simulation algorithms are providing insights into molecular behavior that are accelerating drug discovery and materials design. But perhaps the most significant development is how quantum technologies are changing our approach to computational problems themselves. Classical algorithms are designed to find the correct answer through a series of logical steps. Quantum algorithms are designed to explore the landscape of possibilities and converge on the most probable solution through interference and entanglement. This difference in approach often leads to solutions that are not just faster, but qualitatively different from those found through classical methods. Quantum algorithms might discover unexpected symmetries in optimization problems, reveal hidden correlations in datasets, or identify novel approaches to molecular design that no classical algorithm would ever explore. As you contemplate this shift in computational thinking, notice how it might parallel changes in your own problem-solving approaches. When faced with complex decisions, do you methodically analyze each option sequentially, or do you sometimes allow multiple possibilities to exist simultaneously in your mind until one emerges as clearly preferable? The quantum approach to computation mirrors this more intuitive, holistic style of thinking. While quantum computing captures most of the attention in popular discussions of quantum technology, quantum sensing represents an equally transformative application that's already beginning to impact daily life. The same principles that enable quantum computers to explore multiple computational paths simultaneously can be used to detect physical phenomena with unprecedented sensitivity and precision. Traditional sensors work by measuring changes in classical properties like electrical resistance, magnetic field strength, or optical intensity. These measurements are limited by fundamental noise sources that cannot be eliminated through better engineering. Quantum sensors, by contrast, can approach theoretical limits set by the laws of physics themselves. The semiconductor-superconductor breakthrough enables quantum sensors to be integrated directly into conventional electronic systems. Instead of requiring specialized laboratory equipment operated by expert technicians, quantum sensing capabilities can be embedded in devices that work reliably in real-world environments. Consider the implications for medical diagnostics. Current magnetic resonance imaging systems require powerful superconducting magnets and carefully controlled environments. Quantum magnetometers based on semiconductor superconductors could enable portable MRI systems that provide comparable image quality without the massive infrastructure requirements. The sensitivity improvements are staggering. Quantum magnetometers can detect magnetic fields trillions of times weaker than those measurable with conventional instruments. This level of sensitivity opens up applications that were previously impossible, mapping the magnetic fields generated by neural activity in the brain, detecting underground mineral deposits from surface measurements, monitoring the structural integrity of buildings and bridges through tiny changes in gravitational fields. But the revolution in quantum sensing extends beyond just improved sensitivity. Quantum sensors can measure quantities that have no classical analog. Quantum phase measurements can detect rotation with accuracy that exceeds the best mechanical gyroscopes by orders of magnitude. Quantum correlation measurements can distinguish between signals and noise in ways that classical signal processing cannot match. The integration of quantum sensing into everyday devices is already beginning. Smartphones contain accelerometers and magnetometers that use quantum effects to achieve their sensitivity. Future generations might include quantum gravimeters for indoor navigation, quantum chemical sensors for environmental monitoring, or quantum electromagnetic field sensors for detecting wireless signals with extraordinary precision. This proliferation of quantum sensing capabilities will create what researchers call a quantum-enhanced measurement infrastructure. Instead of living in a world where we can only measure what classical physics allows, we'll inhabit an environment where the fundamental quantum properties of matter and energy become accessible to direct observation and manipulation. Take a breath and imagine what this quantum-enhanced awareness might feel like. Your device is capable of detecting phenomena that are currently invisible. Your environment monitored with precision that reveals patterns and relationships that were previously hidden. Your understanding of the physical world expanded through access to information that transcends classical measurement limitations. As quantum technologies mature beyond computation and sensing, they're beginning to transform communication in ways that challenge our basic assumptions about information transfer and network security. The quantum communication networks, enabled by semiconductor superconductors, operate according to principles that have no classical equivalent. In classical communication, information is encoded in signals that travel from sender to receiver. These signals can be intercepted, copied, or modified without the knowledge of the communicating parties. Security depends on mathematical complexity that might be breakable with sufficient computational resources. Quantum communication works differently. Information is encoded in quantum states that cannot be copied or observed without being fundamentally altered. Any attempt to intercept quantum communications necessarily leaves detectable traces. Security is guaranteed not by mathematical complexity, but by the fundamental laws of physics. The practical implementation of quantum communication has been limited by the fragility of quantum states and the difficulty of maintaining coherence over long distances. Quantum signals degrade rapidly when transmitted through conventional optical fibers. Repeaters and amplifiers that work for classical signals destroy quantum information. The semiconductor superconductor breakthrough addresses these limitations by enabling quantum communication devices that can be manufactured using conventional semiconductor processes. Instead of requiring exotic materials and specialized fabrication techniques, quantum transmitters and receivers can be produced in the same facilities that manufacture conventional electronics. This manufacturing compatibility is accelerating the deployment of quantum communication networks. Instead of building entirely separate infrastructure, quantum communication capabilities can be integrated into existing fiber optic networks. Classical and quantum signals can share the same physical channels, multiplexed in ways that preserve the security properties of both. Early quantum communication networks are already operational in several countries. Banks use quantum key distribution to secure high-value financial transactions. Government agencies employ quantum communication for sensitive diplomatic and military communications. Research institutions share quantum entanglement across continental distances to enable distributed quantum computing experiments. But the long-term vision extends far beyond these specialized applications. As quantum communication becomes more affordable and more reliable, it might eventually replace classical communication for applications where security is paramount. Medical records, legal documents, personal communications, financial transactions, all could be protected by quantum encryption that is fundamentally unbreakable. The implications go beyond security to include new forms of distributed computation and collective intelligence. When quantum entanglement can be shared reliably across global distances, when quantum correlations can be maintained between devices in different continents, entirely new architectures for information processing become possible. Imagine networks where computation is distributed not just across multiple processors, but across quantum systems that share entangled states. Problems too complex for any individual quantum computer could be solved collaboratively by quantum processors that remain quantum mechanically correlated despite being physically separated by thousands of miles. The success of gallium-doped germanium in bridging quantum and classical domains has inspired researchers to explore other materials combinations that might exhibit similar properties. The field of quantum materials engineering is expanding rapidly, driven by the recognition that the right materials can enable entirely new categories of technological capabilities. Traditional materials science focused on optimizing known properties like strength, conductivity, or thermal resistance. Quantum materials science seeks to engineer properties that emerge from quantum mechanical effects. Superconductivity, quantum magnetism, topological order, and exotic forms of quantum entanglement all represent materials properties that have no classical analog. The tools for creating these quantum materials are becoming increasingly sophisticated. Molecular beam epitaxy allows researchers to build crystal structures one atomic layer at a time, with unprecedented control over composition and structure. Advanced lithography techniques can pattern materials at nanometer scales. Scanning probe microscopes can manipulate individual atoms to create artificial quantum systems with designed properties. This level of control over matter at the atomic scale is revealing that the boundary between natural and artificial materials is becoming increasingly fluid. Researchers can now create materials that don't exist in nature, with properties that are precisely tailored for specific quantum applications. Some of these artificial quantum materials exhibit properties that seem almost magical from a classical perspective. Metamaterials can bend light in ways that make objects invisible. Topological insulators conduct electricity on their surfaces while remaining insulating in their bulk. Quantum spin liquids maintain quantum coherence at relatively high temperatures. The semiconductor superconductor breakthrough represents just one example of this broader materials revolution. As researchers learn to engineer quantum properties with greater precision, as manufacturing techniques become more sophisticated, as our theoretical understanding of quantum materials deepens, entirely new categories of devices become possible. Future quantum materials might exhibit room temperature superconductivity, enabling lossless power transmission and magnetic levitation without expensive cooling systems. Others might demonstrate quantum coherence that persists for hours or days rather than microseconds, enabling quantum computers that don't require error correction. Still others might exhibit exotic forms of quantum entanglement that enable communication or sensing capabilities we can barely imagine. The pace of discovery in quantum materials is accelerating as artificial intelligence tools are applied to materials design. Machine learning algorithms can explore vast spaces of possible materials, compositions, and predict which combinations might exhibit desired quantum properties. High-throughput synthesis and characterization techniques can test thousands of materials combinations in the time it previously took to study a single system. As you reflect on this materials revolution, consider how it parallels other forms of creative work. Just as artists combine pigments and techniques to create visual experiences that transcend their individual components, materials scientists are learning to combine atoms and quantum effects to create technologies that transcend the sum of their parts. The simultaneous advancement of quantum computing, quantum sensing, quantum communication, and quantum materials is creating unexpected synergies that are accelerating progress across all domains. Technologies that seemed decades away are suddenly approaching commercial viability as breakthroughs in one area enable rapid progress in others. Quantum computers benefit from improved quantum sensors that can monitor and correct errors in real time. Quantum communication networks become more practical when they can leverage quantum computers for encryption and decryption. Quantum materials research advances more rapidly when quantum simulations can predict the properties of new compounds before they're synthesized. This convergence is creating what complexity theorists call an emergence cascade, where the interaction of multiple advancing technologies produces capabilities that exceed what any individual technology could achieve alone. The whole becomes not just greater than the sum of its parts, but qualitatively different from anything that existed before. The economic implications of this convergence are staggering. Industries that seemed unrelated to quantum technologies are discovering that quantum capabilities can provide decisive, competitive advantages. Financial services firms use quantum optimization for portfolio management. Pharmaceutical companies employ quantum simulation for drug discovery. Logistics companies apply quantum algorithms to supply chain optimization. The semiconductor superconductor breakthrough is particularly significant because it provides a common platform that can support multiple quantum technologies simultaneously. Instead of requiring separate development paths for quantum computing, sensing, and communication, researchers can leverage shared materials and manufacturing techniques across all domains. This platform convergence is dramatically reducing the cost and complexity of quantum technology development. Companies can amortize research and development costs across multiple applications. Manufacturing facilities can serve multiple markets. Expertise developed in one quantum domain can be applied to others. But the deeper significance lies in how this convergence is changing our relationship with technology itself. Instead of discrete devices that perform specific functions, we're moving toward integrated systems that combine multiple quantum capabilities in seamless ways. Imagine devices that combine quantum computation for optimization, quantum sensing for environmental monitoring, and quantum communication for secure data transmission. Instead of carrying separate tools for different functions, you might have access to quantum-enhanced capabilities that adapt dynamically to your needs. This integration extends beyond individual devices to entire technological ecosystems. Smart cities might employ quantum sensor networks for traffic optimization, quantum computers for resource management, and quantum communication for secure coordination between systems. The boundaries between different technologies become fluid as quantum effects enable new forms of integration and coordination. Take a moment to consider how this technological convergence might mirror convergences in your own experience. The integration of different skills, perspectives, and capabilities in your work or creative endeavors. The way different aspects of your personality or knowledge come together to create insights that exceed what any individual component could achieve alone. As quantum technologies become more sophisticated and more interconnected, they're beginning to enable forms of distributed intelligence that transcend the boundaries of individual devices, organizations, or even species. This remains largely speculative, But the mathematical foundations and early experimental demonstrations suggest possibilities that are both profound and transformative. Consider how classical networks enable forms of collective intelligence. The internet allows millions of people to collaborate on projects like Wikipedia or contribute to scientific research through citizen science platforms. Social media enables the rapid spread of information and the coordination of collective action. Search engines aggregate and organize human knowledge in ways that make information accessible on unprecedented scales. Quantum networks might enable even more sophisticated forms of collective intelligence. When quantum entanglement can be shared across global distances, when quantum correlations can persist between systems despite physical separation, entirely new architectures for information processing and decision-making become possible. Some researchers speculate that quantum networks might enable forms of distributed computation, where the boundary between individual processors becomes meaningless. Instead of discrete computers solving problems independently, quantum systems might solve problems collectively through shared entangled states that span multiple physical locations. This possibility remains highly speculative, with no scientific consensus on its feasibility. But the mathematical structure of quantum mechanics does allow for correlations and information sharing that have no classical equivalent. Whether these quantum properties can be scaled up to enable macroscopic forms of collective intelligence remains an open question. The implications extend beyond computation to include new forms of sensing and awareness. When quantum sensors can share entangled states across vast distances, they might be able to detect patterns and phenomena that would be invisible to individual sensors. Distributed quantum sensing networks might reveal correlations in global environmental data, detect subtle changes in gravitational fields, or monitor electromagnetic phenomena with unprecedented precision. But perhaps the most intriguing possibility is how quantum technologies might change our understanding of consciousness and intelligence themselves. If consciousness emerges from complex information processing in biological systems, and if quantum effects play a role in biological information processing, then quantum technologies might provide new tools for understanding and augmenting consciousness. This remains purely speculative, with no established scientific basis. The relationship between consciousness and quantum mechanics is one of the most controversial topics in both physics and neuroscience. But as quantum technologies become more sophisticated, as our understanding of biological quantum effects improves, these questions might transition from philosophical speculation to empirical investigation. Take a breath and imagine what it might feel like to participate in forms of collective intelligence enabled by quantum technologies. Not losing your individual identity, but finding it enhanced through connection to larger patterns of information and awareness. Not being controlled by external systems, but discovering new forms of collaboration and coordination that respect individual autonomy while enabling collective capabilities. As quantum technologies transition from laboratory curiosities to commercial realities, they bring with them ethical challenges that society is only beginning to recognize and address. The same capabilities that make quantum computers so powerful also make them potentially dangerous in the wrong hands. The same quantum properties that enable unprecedented security also create new vulnerabilities. The cryptographic implications alone are staggering. Current internet security depends on mathematical problems that are effectively unsolvable with classical computers. Public key encryption, digital signatures, blockchain technologies all rely on the assumption that certain calculations would take classical computers longer than the age of the universe to complete. Quantum computers could potentially solve these problems in minutes or hours rather than eons. This capability doesn't exist yet, but the timeline for its development is uncertain. Some experts predict it within a decade, others suggest it might take much longer, but the consensus is that it's a matter of when, not if. This creates what cryptographers call the Y2Q problem, a reference to the Y2K concerns that preceded the year 2000. Organizations must transition to quantum-resistant encryption before large-scale quantum computers become available. But predicting exactly when that transition needs to be complete is impossible. The challenge is compounded by the long lifetime of encrypted data. Information encrypted today might still be sensitive decades from now. Adversaries with access to quantum computers could decrypt historical communications, revealing secrets that were thought to be permanently protected. But the ethical challenges extend beyond cryptography to include questions about access, equity, and the concentration of technological power. Quantum technologies require substantial investments in research, development, and manufacturing. They demand expertise that is currently scarce and expensive to develop. This creates the risk that quantum advantages might be available only to wealthy nations and large corporations, exacerbating existing inequalities rather than democratizing advanced capabilities. The quantum divide could become more significant than the digital divide, with quantum haves and have-nots separated by technological capabilities that provide decisive advantages in everything from financial markets to scientific research. There are also questions about the environmental impact of quantum technologies. Many current quantum computers require cooling to temperatures near absolute zero, consuming substantial amounts of energy. As quantum systems scale up, as they become more widely deployed, their energy requirements could become environmentally significant. The semiconductor superconductor breakthrough addresses some of these concerns by making quantum technologies more energy efficient and more compatible with existing manufacturing infrastructure. But it also raises new questions about the responsible development and deployment of quantum capabilities. As you consider these ethical challenges, reflect on how they mirror ethical questions in other domains. How do we balance innovation with security? How do we ensure that powerful technologies serve broad human interests rather than narrow commercial or national advantages? How do we manage transitions to new technological paradigms in ways that minimize disruption and maximize benefits? The governance of quantum technologies presents unique challenges that existing regulatory frameworks are not equipped to address. Unlike many previous technologies that developed gradually over decades, quantum capabilities are advancing rapidly across multiple domains simultaneously. The traditional approach of regulating technologies after they become commercially available might not be adequate for managing quantum risks and opportunities. Quantum technologies also transcend traditional boundaries between different regulatory domains. Quantum computers are simultaneously computing devices, scientific instruments, and potentially dual-use technologies with both civilian and military applications. Quantum sensors can be environmental monitors, medical devices, or surveillance tools depending on how they're deployed. International coordination adds another layer of complexity. Quantum technologies are being developed simultaneously in multiple countries, each with different regulatory approaches and strategic priorities. The global nature of quantum research means that restrictions in one jurisdiction might simply shift development to others rather than addressing underlying risks. Some experts advocate for proactive governance approaches that anticipate future capabilities rather than reacting to current developments. This might involve international agreements on quantum research ethics, standards for quantum technology safety and security, or frameworks for sharing quantum capabilities in ways that benefit all humanity. Others argue that premature regulation could stifle innovation and prevent beneficial applications from being developed. They point to the unpredictable nature of technological development and the difficulty of predicting which quantum capabilities will prove most significant. The semiconductor superconductor breakthrough exemplifies these governance challenges. The same materials and manufacturing techniques that enable beneficial quantum applications could also accelerate the development of quantum technologies that pose security risks. How should governments balance the benefits of open scientific research with the need to prevent dangerous applications? These governance questions don't have easy answers, but they require thoughtful consideration as quantum technologies continue to advance. The decisions made in the next few years about how to regulate, coordinate, and deploy quantum capabilities will shape their impact on society for decades to come. Take a moment to consider how you might want these governance questions to be resolved. What values should guide the development of quantum technologies? How should decisions be made about which applications to pursue and which to restrict? How can diverse perspectives and interests be represented in quantum governance discussions? Beyond the technical capabilities and economic implications, quantum technologies are beginning to influence culture and consciousness in subtle but significant ways. The quantum worldview challenges many assumptions that have shaped human thinking for centuries, introducing concepts like superposition, entanglement, and observer effects that have no equivalents in everyday experience. As quantum technologies become more widespread, as quantum thinking becomes more familiar, these concepts are beginning to influence how people think about other domains. Business strategists discuss organizational superposition, where companies explore multiple strategic directions simultaneously. Psychologists explore therapeutic approaches based on quantum metaphors, though these remain speculative and unproven. Artists create works that explore themes of uncertainty, correlation, and the role of observation in shaping reality. This cultural influence operates through multiple channels. Educational systems are beginning to introduce quantum concepts at earlier ages, helping students develop intuitions for quantum thinking alongside classical logic. Popular media increasingly incorporates quantum themes, making quantum concepts part of common discourse. Professional development programs teach quantum-inspired approaches to problem-solving and decision-making. The language itself is evolving to accommodate quantum concepts. Terms like entanglement, coherence, and superposition are acquiring metaphorical meanings that extend far beyond their original physics contexts. These linguistic changes reflect deeper shifts in how people think about relationships, possibilities, and the nature of reality itself. But this cultural transformation also raises questions about the appropriate boundaries between scientific concepts and their metaphorical applications. Quantum mechanics is a precise mathematical theory with specific domains of validity. When quantum metaphors are applied to psychological, social, or spiritual phenomena, it's important to distinguish between scientifically supported applications and purely analogical uses. Some critics worry that popular quantum culture might lead to misunderstandings about the actual science, creating confusion between quantum physics and pseudoscientific claims. Others argue that quantum metaphors can provide valuable conceptual tools for thinking about complexity and uncertainty, even when applied outside their original scientific context. The semiconductor superconductor breakthrough contributes to this cultural transformation by making quantum technologies more accessible and more integrated into everyday life. As quantum capabilities become embedded in common devices, as quantum thinking becomes more practical and less exotic, the cultural influence of quantum concepts is likely to accelerate. Consider how quantum concepts might already be influencing your own thinking. Do you sometimes hold multiple possibilities in mind simultaneously before making decisions? Do you notice how observation changes your experience of situations? Do you recognize correlations and connections that seem to transcend simple cause and effect relationships? As we approach the end of our exploration, it's worth stepping back to consider the quantum revolution from the perspective of historical time. The journey from the initial discovery of quantum effects to their technological application has spanned more than a century, involving thousands of researchers across multiple generations. The foundational insights of quantum mechanics emerged in the early 20th century through the work of physicists like Planck, Einstein, Bohr, Heisenberg, and Schrödinger. These early pioneers were primarily concerned with understanding the fundamental nature of matter and energy, not with developing practical applications. The mathematical framework of quantum mechanics was largely complete by the 1930s, but its technological implications remained largely theoretical for decades. The development of lasers in the 1960s and semiconductor electronics in the following decades demonstrated that quantum effects could be harnessed for practical purposes, but these applications exploited only simple aspects of quantum behavior. The current quantum revolution began in the 1980s and 1990s with theoretical work on quantum computing and quantum cryptography. Researchers demonstrated that quantum systems could, in principle, solve certain problems exponentially faster than classical computers and provide forms of security that were guaranteed by physical laws rather than mathematical complexity. The transition from theoretical possibility to practical reality has accelerated dramatically in the past 2 decades. Quantum computers have evolved from thought experiments to laboratory demonstrations to early commercial systems. Quantum communication networks have progressed from proof-of-concept experiments to operational deployments. Quantum sensors have advanced from research curiosities to commercial products. The semiconductor superconductor breakthrough represents a particularly significant milestone in this historical trajectory because it addresses one of the fundamental barriers that has limited quantum technologies since their inception. By enabling quantum components to be manufactured using conventional semiconductor processes, it bridges the gap between exotic laboratory demonstrations and scalable commercial production. This historical perspective reveals something profound about the relationship between scientific discovery and technological application. The quantum effects that are now enabling revolutionary technologies were first observed in careful laboratory experiments over a century ago. The mathematical frameworks that describe these effects were developed by researchers who had no idea their work would eventually lead to practical devices. This suggests that the most transformative technologies often emerge not from directed engineering efforts, but from patient investigation of fundamental phenomena. The researchers who first studied quantum mechanics were driven primarily by curiosity about the nature of reality. Their discoveries are now reshaping entire industries and creating new forms of human capability. As you contemplate this temporal perspective, notice how it mirrors other forms of patient development in your own experience. Skills that seem to emerge suddenly often build on years of accumulated practice. Insights that appear as sudden revelations usually integrate understanding that has been developing gradually over extended periods. The quantum revolution we've been exploring represents the culmination of generations of accumulated understanding, but it also opens doorways to possibilities that are only beginning to emerge. The semiconductor superconductor breakthrough is not an endpoint, but a new beginning, a foundation for developments that will unfold over the coming decades. Perhaps most remarkably, the quantum technologies we've been discussing are transforming not just our external capabilities, but our understanding of what it means to live in a quantum universe. Every quantum processor that achieves stable operation, every quantum sensor that detects previously invisible phenomena, every quantum communication link that demonstrates secure information transfer adds to our collective appreciation of the quantum nature of reality. We are becoming a species that can consciously interact with quantum mechanical effects. This transition from passive observers of quantum phenomena to active participants in quantum processes represents a profound shift in humanity's relationship with the fundamental laws of nature. The universe that once seemed mechanically predictable is revealing itself to be far more mysterious, more responsive, more alive with possibility than our classical intuition suggested. The manufacturing precision required to create semiconductor superconductors teaches us about the delicate balance between order and chaos that enables complex systems to emerge and persist. The coherence times achieved by optimized quantum processors demonstrate how information and consciousness might maintain their integrity even in the presence of noise and disturbance. The entanglement correlations that enable quantum communication reveal how connection and correlation can transcend the limitations of space and time. These technological achievements are not separate from human consciousness, but expressions of it. The same intelligence that contemplates the mysteries of quantum mechanics is learning to embody those mysteries in practical devices. The same awareness that puzzles over the nature of observation and measurement is developing technologies that make observation and measurement more precise and more powerful. There's something deeply satisfying about this convergence between understanding and capability. For too long, the most profound insights of physics remained locked away in mathematical formalism, accessible only to specialists who could navigate complex equations and abstract theories. Quantum technologies are beginning to make these insights tangible, experiential, available to anyone who interacts with quantum-enhanced devices. When you use a quantum sensor to navigate underground where GPS signals cannot reach, you are directly experiencing the sensitivity that emerges from quantum superposition and entanglement. When you communicate through quantum encryption that is guaranteed by physical laws rather than mathematical complexity, you're participating in the non-local correlations that Einstein found so troubling. When you benefit from drugs discovered through quantum molecular simulation, you're touching the quantum mechanical processes that govern all of chemistry and biology. This experiential access to quantum phenomena is changing how we relate to the concepts themselves. Superposition is no longer just an abstract mathematical principle, but a practical resource for computation and sensing. Entanglement is no longer just a philosophical puzzle, but a communication protocol, and a coordination mechanism. Uncertainty is no longer just a limitation on knowledge, but a source of possibility and creativity. There's a beautiful recursive quality to how quantum technologies are accelerating their own development. Quantum computers are being used to design better quantum computers. Quantum simulations are revealing new quantum materials that enable more sophisticated quantum devices. Quantum sensors are providing the precision measurements needed to optimize quantum manufacturing processes. This recursive bootstrap is creating a positive feedback loop where each advance in quantum capability enables faster progress toward the next advance. The learning curve is not linear, but exponential, with each generation of quantum technologies providing tools that accelerate the development of the next generation. The semiconductor superconductor breakthrough is particularly significant in this recursive dynamic because it provides a platform that can support multiple quantum technologies simultaneously. Instead of requiring separate optimization efforts for quantum computing, sensing, and communication, researchers can leverage shared advances in materials science and manufacturing techniques across all domains. This platform convergence is dramatically accelerating the pace of quantum innovation. Techniques developed for optimizing quantum processor coherence can be applied to quantum sensor design. Manufacturing processes refined for quantum communication devices can be used to produce quantum computing components. Error correction algorithms developed for quantum computers can enhance the reliability of quantum sensors. But the recursive quality extends beyond technical optimization to include human learning and understanding. As quantum technologies become more sophisticated, they provide new tools for studying quantum phenomena. As our understanding of quantum mechanics deepens, we can design better quantum technologies. As quantum thinking becomes more natural and intuitive, we can conceive of applications that would not have occurred to us from a purely classical perspective. This recursive relationship between understanding and capability suggests that we might be entering a period of accelerating insight as well as accelerating technology. Each advance in quantum capability reveals new aspects of quantum reality. Each new understanding of quantum phenomena suggests new technological possibilities. Take a moment to consider how this recursive dynamic might apply to your own learning and development. How do improved capabilities enable better understanding? How does deeper understanding suggest new possibilities for action? How might this feedback loop between knowledge and skill accelerate your own growth and effectiveness? As quantum technologies become more widespread and more integrated into daily experience, something subtle but significant is beginning to happen. People who work regularly with quantum systems are developing what might be called quantum intuition, an ability to think naturally in quantum terms without conscious effort or translation from classical concepts. This quantum intuition manifests in various ways. Quantum engineers begin to anticipate how changes in one part of a quantum system will affect distant components through entanglement correlations. Quantum algorithm designers start to think in terms of probability amplitudes and interference patterns rather than sequential logical operations. Quantum materials scientists develop intuitive understanding of how atomic arrangements create emergent properties that have no classical analogue. This development of quantum intuition represents more than just professional expertise. It suggests that human consciousness is adaptable enough to internalize quantum concepts as natural ways of thinking about reality. The strange becomes familiar through repetitive exposure and practical engagement. The implications extend beyond technical domains to influence how people approach complex problems in other areas. Quantum thinking emphasizes superposition of possibilities rather than premature commitment to single solutions. It appreciates the role of observation and measurement in shaping outcomes rather than treating them as passive revelation of pre-existing facts. It recognizes correlation and entanglement as fundamental aspects of complex systems rather than coincidental connections. These quantum-inspired approaches to thinking and problem-solving are beginning to influence fields as diverse as business strategy, therapeutic practice, educational methodology, and artistic creation. Not because quantum mechanics directly applies to these domains, but because quantum concepts provide useful metaphors and frameworks for navigating uncertainty and complexity. The semiconductor superconductor breakthrough contributes to this development of quantum intuition by making quantum technologies more accessible and more reliable. When quantum effects can be controlled through conventional electronic interfaces, when quantum measurements provide clear and consistent results, when quantum algorithms solve practical problems with predictable efficiency, quantum thinking becomes more concrete and more actionable. As you reflect on your own relationship with uncertainty and possibility, notice whether quantum concepts resonate with your existing intuitions. Do you sometimes feel that observing a situation changes its dynamics? Do you recognize correlations that seem to transcend simple cause and effect? Do you find value in maintaining multiple possibilities simultaneously rather than forcing premature closure? The quantum revolution we've been exploring carries implications that extend far beyond technology into the deepest questions of philosophy. What is the nature of reality? What is the relationship between mind and matter? What does it mean to know something? How do possibilities become actualities? For centuries, Western philosophy has been dominated by what might be called the classical worldview. Reality consists of objects with definite properties existing independently of observation. Cause and effect operate through direct mechanical interactions. Knowledge involves discovering truths that exist independently of the knowing process. Quantum mechanics challenges each of these assumptions. Objects do not have definite properties independent of measurement. Cause and effect operate through non-local correlations that transcend mechanical interaction. Knowledge emerges through participatory processes that shape what can be known. These challenges to classical assumptions have inspired new philosophical frameworks that attempt to integrate quantum insights with traditional questions about the nature of existence, consciousness, and knowledge. While these frameworks remain speculative and lack scientific consensus, they illustrate how quantum technologies might influence our understanding of fundamental philosophical questions. Some interpretations suggest that consciousness and quantum mechanics might be more intimately related than classical physics allowed. If observation plays a fundamental role in quantum measurement, if information and awareness are basic constituents of reality, if the boundaries between observer and observed are more fluid than classical physics suggested, then consciousness might be understood as a quantum phenomenon rather than an emergent property of classical matter. These possibilities remain highly speculative, with no established scientific foundation. The relationship between consciousness and quantum mechanics is one of the most controversial topics in both physics and philosophy. But the questions themselves are significant even if definitive answers remain elusive. The semiconductor superconductor breakthrough contributes to these philosophical discussions by making quantum technologies more accessible to direct experience. When quantum effects become part of everyday technology, when quantum concepts become part of common discourse, when quantum thinking becomes part of practical problem solving, the philosophical implications of quantum mechanics become more immediate and more relevant. As you contemplate these philosophical questions, notice how they might appear in your own experience. What is the relationship between your awareness and the reality you observe? How does the act of paying attention change what you notice? What is the boundary between your inner experience and the external world? As we near the completion of our journey through the quantum landscape, it's worth considering how the developments we've explored fit into the larger story of human development and cosmic evolution. The quantum revolution represents not just a technological transition, but a maturation of human consciousness, an expansion of our capacity to understand and work with the fundamental principles that govern existence. From this perspective, the semiconductor superconductor breakthrough is one move in what game theorist James Cass called an infinite game, a form of play where the purpose is not to win, but to continue playing, not to reach a final destination, but to keep the possibilities open. The quantum technologies we're developing are not endpoints, but tools for exploring ever deeper levels of reality and ever greater possibilities for creative expression. The recursive quality we noted earlier, where quantum technologies accelerate their own development, suggests that we might be entering a phase of open-ended exploration, where each discovery reveals new horizons rather than approaching final answers. The more we learn about quantum mechanics, the more mysterious and wonderful it becomes. The more sophisticated our quantum technologies become, the more possibilities they reveal for applications we haven't yet imagined. This open-ended quality extends beyond quantum technologies to include their interaction with other advancing fields. Artificial intelligence is becoming more sophisticated at the same time that quantum computers are becoming more powerful. Biotechnology is revealing the quantum mechanical basis of life processes, while quantum sensors are providing new tools for studying biological systems. Nanotechnology is enabling atomic scale engineering, while quantum effects are suggesting new possibilities for materials design. The convergence of these advancing fields creates what complexity theorists call an adjacent possible, a space of near-term potential that expands as capabilities develop. Each advance in any field enlarges the space of what becomes possible in other fields. The boundaries between different domains of knowledge and capability become increasingly permeable. This suggests that we might be approaching what some researchers call a technological singularity, though not necessarily in the dramatic sense often portrayed in science fiction. Rather, we might be entering a period where the pace of change accelerates to the point where prediction becomes impossible and adaptation becomes the primary survival skill. But whether or not such dramatic transitions occur, the quantum revolution we've been exploring represents a profound expansion of human capability and understanding. We are becoming a species that can consciously participate in quantum mechanical processes, that can design and control matter at the atomic level, that can harness the strange properties of quantum reality for practical purposes. Take a final breath and consider what this expansion of human capability might mean for you personally. How might quantum technologies touch your life in the coming years and decades? How might quantum thinking influence your approach to uncertainty, possibility, and observation? How might the ongoing quantum revolution create opportunities for learning, growth, and creative expression that don't yet exist? Even as we develop increasingly sophisticated answers to questions about quantum reality, new and deeper questions continue to emerge. Why do the mathematical structures that describe quantum mechanics correspond so precisely to physical phenomena? What determines which of many possible quantum interpretations, if any, correctly describes the nature of reality? How do classical properties emerge from quantum processes in biological and psychological systems? These questions remind us that scientific understanding is not a finite resource that can be exhausted, but an infinite process of discovery that reveals new mysteries as it resolves old ones. The quantum technologies we're developing don't eliminate mystery from the universe. Instead, they give us new tools for engaging with mystery at deeper levels. The semiconductor superconductor breakthrough we've been exploring exemplifies this relationship between answers and questions. By solving the manufacturing challenges that limited quantum technologies, it opens up new possibilities for investigation and application. Each problem solved reveals new problems to be solved. Each capability achieved suggests new capabilities to be developed. This endless unfolding of questions and possibilities is not a flaw in the scientific process, but its greatest strength. Science progresses not by reaching final answers, but by asking better questions. Quantum mechanics has given us a framework for asking questions about reality that were inconceivable from classical perspectives. As quantum technologies become more sophisticated, they will undoubtedly reveal phenomena and possibilities that we cannot currently imagine. The same way that classical technologies eventually revealed quantum effects that were invisible to pre-technological investigation, quantum technologies will likely uncover new layers of reality that are currently hidden from view. And so we find ourselves at the threshold of a new age, one that's arriving not with dramatic fanfare, but with the quiet precision of atoms arranging themselves into extraordinary patterns. The gallium-doped germanium breakthrough we've explored tonight represents far more than a manufacturing innovation. It's a bridge between worlds, a materials manifestation of humanity's growing ability to work consciously with the quantum foundations of reality itself. As you settle into whatever quiet surrounds you now, carry with you the understanding that the quantum revolution is not something happening to us, but something we are actively creating through patient investigation, careful engineering, and the simple act of remaining curious about the deepest layers of existence. The future we've glimpsed together is being written one atomic layer at a time, in laboratories around the world where the impossible becomes routine and the mysterious becomes practical. Remember that you are not separate from this unfolding story. You are woven into it, a temporary pattern of quantum fields, contemplating their own nature, participating in the universe's ongoing conversation with itself. The semiconductor breakthrough is just one verse in an infinite poem of possibility, and the next chapters are waiting to be discovered. Sweet dreams from the quantum realm, where even the act of observation changes what's possible. If you found yourself wondering about the deeper connections between consciousness and quantum mechanics, you might enjoy exploring, could quantum entanglement be the hidden science behind manifestation? Until our paths cross again in the vast landscape of knowledge, keep wondering, keep questioning, and remember that in a quantum universe, the future remains beautifully, mysteriously unwritten.